All right, let's take a look at the first derivative test. Let's say that we have this function f of x equal 3x to the third minus 3 halves x squared. One thing we know about maximums and minimums is that they happen at critical points. So the first thing that we should do is try and find where the critical points of f of x are. Critical points happen when the derivative is either equal to 0 or undefined. So we take a look at the derivative of f of x, which will happen at 9x squared minus 3x. This function is never going to be undefined because it's a polynomial. However, it will equal 0. So I'm going to set it equal to 0 and solve. Factor out that 3x, I'm left with 3x minus 1. So obviously my critical numbers are going to happen at x equals 0 and at x equals 1/3. What we want to be able to do is to use the first derivative to help us determine whether maximums or minimums happen at 0 or at 1/3. So we're going to have to use a sign chart. Right now, I know that my derivative is 0 in two different places, at 0 and at 1/3. So I'm going to go back and look at f prime in terms of 3x times 3x minus 1. And I'm going to use this to test each interval. So on the interval where x is less than 0, then that would mean that 3x is negative. And 3x is again negative, minus 1 would still be negative. So I'm going to take a negative number times a negative number, meaning that on this interval, my derivative is positive. Then I'm going to test in between 0 and 1/3. Now there's not much in there, but if I took halfway, that would be the number 1/6. So looking at f prime of 1/6, well, 3 times 1/6 is a positive number. And 3 times 1/6, that is actually a half, and a half minus 1 would be negative. So positive times negative means that every derivative on this interval will be negative. After the 1/3, we could pick any number out there, even if it's a billion, and test it. 3 times a billion is positive, and 3 times a billion minus 1 is also positive. So we'll have positive times a positive, meaning that all the derivatives past 1/3 are all going to be positive. Now, how does this help us? Since this is our sign chart for the derivative of f, this is telling us the slope of the tangent lines are positive and then negative and then positive. If all of the derivatives are positive on an interval, that means that the original function is going to be increasing. Then when x is equal to 0, it has a tangent line with a slope of 0, so it flattens out. Then on the next interval, since the derivative is negative, the original function is going to be decreasing until it gets to 1/3 when this derivative is 0. So the slope of the tangent line is 0. That's when the function is going to turn around, and since the derivative is positive, the original function is going to end up increasing again. Thinking about the original function based on its derivative tells us where all of the extrema are. We can see that we're going to have a relative maximum when x is equal to 0, and that's because the derivative changes from positive to negative. A relative minimum is going to happen when x is at 1/3, and that's because the derivative changes from negative to positive. In essence, that's what the first derivative test is. Technically, the first derivative says that if c is a critical number of f of x, then if f prime changes from positive to negative at c, so looking at a sign chart, if we know that derivative is 0 or undefined at c, and it changes from positive to negative, then the original function went from increasing to decreasing. So we have this kind of shape on the original function. Therefore, this has to be a relative maximum. Of course, if it's the opposite, if f prime changes from negative to positive at c, so at c, it went from negative to positive, that means the original function went from decreasing, turned around, and then went to increasing. that would mean that down here is a relative minimum. If it doesn't change sign, so that means that, maybe we have a derivative of 0 or it's undefined at C, and it went from positive to positive, or it went from negative to negative. And then what happened is the original function was increasing, and then it had a vertical tangent line for just a second, and it continued to increase. That means that this point is not going to be a maximum or a minimum. Similarly, if it was decreasing and then had a vertical tangent line here and continued to decrease, we could see that it's neither a maximum nor a minimum. So let's try a few more examples. Let's take g of x is equal to x plus 2 squared times x plus 1. Our first step is to find the critical numbers. So we have to look at the derivative. Since we're taking the product of two things, we have to use product rule, which says 1 d2, so derivative of x plus 1 is just 1, plus 2 d1. And so since x plus 2 squared is a chain rule, we have to take the derivative of the squared, which would be 2 times x plus 2 to the first, and then multiply by the derivative of what's inside, which is just 1. And we're going to have to simplify this thing. So we have x plus 2 squared is this first term, plus 2 times x plus 1 times x plus 2. I can factor out one of those x plus 2's out of each term, and from here I'll still have an x plus 2, and from the second half I'll have 2 times x plus 1. And this will simplify to x plus 2 times 2x plus x is 3x, and 2 plus 2 is 4. I like it factored like that because if we're going to identify those critical numbers, we want to find out when the derivative is 0 or undefined. This is a polynomial. It'll never be undefined, but it will equal 0. And it will equal 0 when x is negative 2 or when x is negative 4/3. Our next step is to make a sign chart for the derivative in order to help us find the maximums and minimums. So my derivative, I'm going to go back to using g of x, is that x plus 2 times 3x plus 4. We can see that our two critical numbers, which we already found, are at negative 2 and negative 4/3. Both of them are going to be when the derivative is equal to 0. And now we start testing intervals. If I pick something smaller than negative 2, like negative 2 billion, negative 2 billion plus 2 is negative, and negative 2 billion times 3 minus 4, that's still going to be negative. Negative times negative is positive. Then we move on to the next interval. In between negative 2 and negative 4/3, our first factor will turn positive, whereas 3x minus 4 will stay negative. So this interval will be negative. And once we go on the positive side of negative 4/3, then both of these factors will be positive, making the entire product positive. We don't need to draw in the original function or any shape of it if we don't want to, but it's good to visualize that because the derivative, this remember is our sign chart for the derivative, but because the derivative is positive, that means the original function is increasing. Then it has a slope of 0, so it stops and turns around and decreases until we get here. And there the derivative will be 0 again, and the function will change to increasing. So just like the last one, here's a general shape for our original function. And now we're down to the last step. And that is to identify the relative maximum and minimum. Of course, we can see from our picture that the relative maximum is going to happen when x is negative 2. That's because the derivative changes from positive to negative. And the relative minimum happens at x equals negative 4/3 because the derivative changes from negative to positive. All right, let's try finding maximums and minimums with the trig function, this time on an open interval. Because it's an open interval, we don't have to worry about endpoints being critical numbers. Instead, we're just, again, going to go back to the derivative. And the derivative of h is going to be 1/2 minus cosine of x. 1/2 minus cosine is never going to be undefined, but it will equal 0. That will be when 1/2 is equal to the cosine of x. And so we think about cosine, and cosine is equal to 1/2 when x is pi over 3. It's also, since we get almost the entire circle, we also have to think about where else on the unit circle is cosine equal to 1/2, and that's when the x-coordinates are positive, so that will be in the fourth quadrant, and the pi over 3 angle in the fourth quadrant is 5 pi over 3. Next, we create our sign chart. We have two critical numbers. One is at pi over 3, and the other one is at 5 pi over 3. For both of these, our derivative is equal to 0. And we want to test the derivative function. H prime is equal to 1/2 minus cosine of x. So we pick something that's smaller than pi over 3. We don't want to, pick negative a billion or anything like that because of the periodic nature of sine of x. So I'm going to pick something that's smaller than pi over 3, but doesn't make it to that negative pi over 3. So I'm going to pick h prime at 0. H prime at 0 would be 1/2 minus the cosine of 0, and the cosine of 0 is 1. So 1/2 minus 1 is negative 1/2, making it negative. Everything on that interval will be negative. In between pi over 3 and 5 pi over 3 is pi. That'll be 1/2 minus the cosine of pi. The cosine of pi is negative 1. So 1/2 minus negative 1 is a positive number, 3/2. So everything is positive here. And then after 5 pi over 3, I'm going to use 2 pi. I know that neither 0 or 2 pi is on our interval. However, we could tell the nature of the derivative by looking at those. So again, 1/2 minus the cosine of 2 pi is the same as 1/2 minus the cosine of 0, which is negative 1/2. So here we are at being negative. Now for the last step of identifying the relative maximums and minimums, when the sign chart for the derivative changes from negative to positive, so it went from decreasing to increasing, that means that a relative minimum happened at x equals pi over 3. When the derivative changes from positive to negative, that means a relative maximum occurred at x equals 5 pi over 3. Let's try one last example. K of x is equal to x squared minus 4 to the 2/3 power. And the first thing we want to do is to find the derivative. So the derivative of k, we're going to have to use chain rule. It would be 2/3 times this to the negative 1/3 power. And then times the derivative of what's on the inside, so that's 2x. Simplifying that, clean it up a little bit. 2x times 2 would be 4x in the numerator. And then we'll have 3 times the cubed root of x squared minus 4. Now that we have a fraction, we do have to worry about when this function is going to be undefined as well as when it's 0. The derivative will equal 0 when the numerator is equal to 0. So that would be when x is 0. The derivative will be undefined when the denominator is equal to 0. And that will only happen when this x squared minus 4 is equal to 0. So we do a little solving real quick, and that'll happen when x is positive or negative 2. So now we have 3 critical numbers that we have to worry about. So let's make a sign chart. We have 3 critical numbers. They're going to happen at 0, and at 2, and at negative 2. And actually for 2 and negative 2, that is when the derivative is undefined. At 0 is when the derivative is equal to 0. So we want to test that on our derivative, k prime, with k prime being 4x over the 3 times the cubed root of x squared minus 4. So we start picking some values. I'm going to pick something smaller than negative 2. All right, so something like, even negative 100. I don't really care about what the values are, but I do know that as I create my fraction, that if I'm using x as negative 100, 4 times negative 100 is negative, 3 is positive, and then I'm going to take the cubed root of negative 100 squared, which is positive and large, minus 4. So that'll stay positive. That looks like this entire fraction will be negative. So on my sign chart, we have something negative. Next, I'm going to test k prime at negative 1. So my fraction will have 4 times negative 1 is negative, 3 is positive, and then I'll have the cubed root of negative 1 squared, which is 1, minus 4. So that's negative. Overall, this entire fraction is going to end up being a positive number. So there we go. K prime of positive 1 will give me a fraction where the numerator is positive, 3 is positive, and then I'm going to take the cubed root of 1 squared minus 4, again being negative. This entire fraction will be negative. After 2, I could pick any number I want, like 100. And 4 times 100 is a positive number. 3 is positive. And then 100 squared minus 4 is going to be positive as well. That means that this derivative will be positive. Great. Now, looking at our sign chart, we can identify where all of the relative maximums and minimums are. Kind of running out of room, but wherever the derivative changed from negative to positive, so from here and here, both of these at negative 2 and 2 are going to be relative minimums. So we have 2 relative minimums at x equals plus or minus 2. The maximum is going to happen when the derivative changes from positive to negative. So that's going to happen when x is equal to 0.